All right, so welcome back. Today we're going to continue, or we're actually going to start on our next module, Module 10, which is simply file I/O. This will be a rather short one, simply because a lot of the stuff that we're going to cover, you already know about it. You know about standard input, you know about standard output, printing to the standard output, you know about standard input a little bit. We just have to do it a little bit differently because the standard input and the standard output are actually files. So when we talk about files, let me do a mic check here really quick. Okay, so when we talk about file I/O though, traditionally a file is a unit of stored memory, usually on disk, right? So when we talk about a file normally, people assume that it's going to be some file on a disk, but that's not the only thing that a file is. In fact, files are also directories, right? Things that you store files in themselves, those are files. Buffers, right? Like standard input, output. Those are files. Because when you sit there and mash the keyboard, what you're actually doing is you're writing to a file. You're writing to the standard input buffer. So as you type your, you mash the keyboard, then letters are being filled up into the buffer, and it's only when you actually call, let's say, scanf or something like that, that the program then takes over and starts actually reading from that buffer, from that file. Likewise, the standard output, it's writing to a file, but it only ever ends up on the console when it gets flushed out, right? So you could have a lot of stuff in there already, and then because file I/O is actually really expensive. So it's whenever the operating system decides, okay, let's go ahead and flush the buffer, or your program forces a flush. Flushing means simply to take whatever is in that output buffer and print it to the actual screen. All right. So there also a socket. It is a file. It could be a file. A program is a file, both a running program and a compiled file that's sitting in there on your disk. But also when it's running, that's a file, right? A lot of things are basically in Unix terminology, everything is a file. Okay. At this point, I would remind you that we are on Piazza live Q&A, and of course, we've got the live chat on YouTube available. All right. Files may be read from, that's input, or written to, that's output. Right, and that's where we get I/O. Right. I for input, O for output, file I/O. Files may be plain text or binary, right? Or plain text, but structured and not intended for human consumption, right? You're going to see a little bit of this in your lab tomorrow when you start working with XML, right? For example, JSON or XML, all right, etc., right? Or base 64 encoding. Right? For example, email is a purely textual-based protocol. How can you send attachments through email? What you do is you take that binary file and you encode it, usually in base 64 or UU encode or something like that. You encode it as a bunch of letters, A through Z, both uppercase, lowercase. In the case of 64, we need 64 symbols. So uppercase and lowercase, that gives us 52. 0 through 9 gives us 10 more. That's 62. And then there are two, I forget what they are, equals and something else. But there are two more symbols that are used. And then you just take this binary file, you encode it as text, and then you send it over a text-based protocol like email. When it opens up on the other end, then and you open it up, what you're actually doing is your email client is decoding that text and then producing the binary file. Right? Try it out next time. Send yourself an image as an attachment, and then on, say, Gmail or something like that, look at the raw email, and you'll see a bunch of garbage encoding of the actual binary file. Okay. We're going to work, of course, with mostly with plain text files. Sometimes we'll work with structured files like XML or JSON. JSON is JavaScript object notation. It's common in web development and even in back-end development now because it's basically a lightweight XML. It's a way of encoding information in a plain text file. Right? The basic steps of working with files are, one, Well, you got to open the file. Right? 2, process the file. Now, if you open it up for reading, then of course you're going to read the file into memory and then process its contents. If you open it up for writing, for output, then you simply just start writing to the output, and that's it. Right? Once you're done with that file, though, you need to make sure that you clean up after yourself. And so if you've opened the file, what do you need to do? Close the file. Right? Now, 99 times out of 100, it'll take care of closing the file for you. Right? When your program is dies. It's that 1% of the time that if you fail to close the file, it'll actually corrupt the contents, or maybe nothing gets written at all. 99% of the time you'll be fine. It's that 1% of the time that it fails that you're gonna kick yourself and realize, oh, I needed to close that file. All right. So let's go ahead and go through these. We won't go in that order simply because the first and the second step are actually really simple. So let's look at opening a file first in C. Right? A file is represented by the file star built into the standard library. Now, what does that tell you? First of all, well, it's all caps right there, first of all. So it is case sensitive. You have to be careful about that. But also, that star denotes that it's a pointer. Why would it make sense for a file to be a pointer? Here's your file, right? If you open it up, where do you start reading from? You start reading at the beginning, the first line, say. Then you read a character or you read a line. What happens to your pointer? It advances to the next line or to the next character. That's why it's a pointer. It's pointing to some memory location where the file is stored. Initially, it's pointing at the beginning of the file. As you read line by line, if there are 4 lines, you read the first line, the pointer moves to the second line. Then the pointer moves to the third line and once you read the second line, etc. It's moving through memory, so it makes sense that it's a pointer. But it's not a pointer that you have to work with directly. To open a file, use fopen. Right? What do you think that stands for? File open, exactly. Function. The fopen function takes 2 arguments. Right? A string representing the path/name of the file you want to open. And the second one, a second string that represents the mode that you want to open it up for. So for example, if you want to read the file, it's going to be R. That's for file input, reading, right? If you want to open the file for writing, then what do you think it is? W, lowercase w. I don't know that it's case sensitive, but I've only ever seen lowercase. And that's for writing or output, right? There are other modes. We're not going to cover them. There's append mode. There's binary mode, read, write, binary mode, stuff like that. We're not going to cover those, right? These are the 2 that we're going to stick with, reading and writing, input and output. It returns a pointer to the file upon success, right? So you would capture that return value so that you can use it when you process the file and eventually close the file. So let's go ahead and take a look at some examples. All right? And to do that, I'm simply going to go over to the CS50 ID here. And let's open up a file for reading. And we'll just open up a data.txt file. Right? So let's open a file in the current directory for reading. There, yeah, I got it. All right. So file star. I'll just call it F. If you want to, you can call it in or input F, input file. Awesome, right? I'll just go ahead and go with in for now. Is equal to a call to fopen. And by the way, fopen and all this stuff is going to be in the standard input-output library that you've already been bringing in. So you don't need to bring anything new in. I want to open up a data.txt file for reading. Right? Let's go ahead and try that. Of course, it's not going to do anything yet because we've only opened it. Let's go ahead and run that. Well, I'm not doing anything, so it's not going to fail. But do you see a data.txt file over here at all? Nope. So let's check. What did we get back? What kind of pointer did we get back? If it failed to open, if it fails to open, what do you think is returned? Null, the only thing that can return because it's returning a pointer. If it fails to open, null is returned. And we can check for that. If in is equal to null, right, then printf failed to open data.txt file. Right, and the line. Right, and then, of course, we can quit or whatever, right? And please enter another file name if it's interactive or something like that. Right there, failed to open the data.txt file because it doesn't exist, right? Now, what if we opened it up for writing? Does it have to exist? I'm creating this file now because I'm going to write to it, right? So when I do something like this, GCC, and I run it for writing now, oh, guess what happened? It created it over here, data.txt. Now, what's in that file? More data.txt, nothing. Right? If I do lsla, I list all of the details of those files, and I look at data.txt. Look at what size is the file? 0 bytes, because you didn't write anything to it. Right? So I'll go ahead and bring these over here as in our example. See, before we do that though, let's open up another file. Let's open up a file somewhere else. Let's see, I don't know. ls etc password. Yep, there it is. Let's open the etc password file. Right? Note here that I am providing a full path. You can provide a relative path. For example, I could go up one level, right? I'm in this code directory right here, and I could go up one level and then down into the archive folder over here and open up, say, setup.sh instead. Setup.sh. Right? Let's try that. Of course, that exists. It's right there. Let's open it up for reading because I don't want to overwrite the contents of the file. But this should be successful. Right? It should print out nothing because, of course, it was able to open up that file, but you didn't do anything with it. I failed to close the file, so I could have ended up corrupting this file over here. Thankfully, I didn't. I fell into the 99% of the time that it took care of it for me. Yay. Right? All right. So you can have relative paths. So open a file using a relative path. Right? Open up a file. Open a file using an absolute path. Right? For this, I'll just use the same thing here, but I'll go to the root of the file system, and there's a directory called etc. We call it etc, but it's short for etc. Right? Just a bunch of miscellaneous stuff, etc. And then there's this file there called passwd. What do you think that stands for? Password file. Okay. Should I be able to open that up? Maybe, maybe not. I do have. I think I technically have. Who am I? I'm not. I'm not root on this thing. Who am I? I think I'm just Ubuntu, which is a special user that they created on these things. Of course, if you are on CSE, no way would you be able to open up sensitive files. But it turns out that the etc password file is not sensitive. If you take a look at it, all these X's, those are passwords that have been redacted. They're no longer stored in the password file. They're stored in a different file, the etc shadow file. Right? Cannot open that, permission denied. Right? Thankfully, right? And so if opening it up for reading or writing fails because you don't have permission, because it doesn't exist, etc., then it will end up being null. Okay? So let's make a note of everything that we just covered here. Opening a file for reading that does not exist or that you do not have permissions to will result in null. And of course you can check for that. Opening a file that does not exist for writing ends up creating the file. Right? Opening up a file that already exists, opening a file that exists for writing will start overwriting the file. So be careful. It's not going to ask you, are you sure that you want to do this? It's just going to open it up and you're going to start overwriting the other file. One of the most common mistakes I see is as follows. Here's my code. Here's my code that I've spent 10 hours on, and I've in this demo.c file, and I've completed it. I checked it into the web grader. Everything works great. I'm going to get an A now, except that I screwed up and file in equals open demo.c for writing, and then I start doing things. Right? What's going to end up happening to my awesome file that I've just completed? It's going to start overwriting it, right? And all the contents of that original file are now gone. There's no undo. There's no undelete. It's just, okay, now I have to put in that 10 hours of work again to rewrite all my code, right? Or I could go back and say, you know, what Burke was right. I should have been using GitHub this entire time. I should have been checking in my code after I was done, and I will do that from now on, right? Make sure that you're doing that. All right, so it will overwrite anything that you open it up for writing, right? Okay. Don't be like me that confuses reading and writing all the time because there are 3 R's, reading, writing, and arithmetic, right? Just remember, W stands for writing, reading stands for R, right? R stands for reading. So it might fail if you don't have permissions, etc. So what about that third step? We're going to skip the second step and jump immediately to the third step because it's the simplest of all. Closing a file. Right? Once you are done with a file, be sure to close it. Right? Failure to close could result in file corruption or it not saving, right? So to close a file, if I used fopen to open a file, what do you think I used to close it? Close. All right. Lots of people just say F close, F open. I like to, you know, put them together like using elision to make it all one word. Fopen and close, right? Use close. Simply pass it the file pointer you want to close, right? So for example, if I opened it up before, if I opened up that password file before, and I want to close it now, I'll ... process the file. Once I'm done with it, I simply do close F. Kind of like free, right? You just pass it the pointer and it takes care of it for you. Okay, there's nothing special there. So the close in, not having read anything, and so I'm pretty confident that this won't do anything because you open it up, you don't write anything, and you close it. Let's find out. Aha! What happened? I opened it up. I started at the beginning of the file. Here's the old contents of the file. I started at the beginning of the file, and then I didn't write anything, and then I closed it. What? So where is it closing? It's closing at the beginning of the file. What happens to all this stuff that I had there? Lost and gone forever. Be careful, right? This is exactly what I was illustrating before. We didn't lose much. All I did was just undo, right? But there is no undo in general. So be careful. Right? In fact, I'm going to be so careful, I'm going to go ahead and get rid of that old a.out file immediately so I don't do that again. Right? And let's open up a different file. What do I want? Data.txt. Okay, for writing. So that's closing a file, opening a file, closing a file. Now we'll look at file output because that's simpler than file input. So file output. So you know how to do this already. There are actually dozens of ways of doing file output. I'm going to show you the easiest one way of doing it. Right? To keep it simple, just use printf. So we all know what printf is, print formatted. What is that extra F in front of it? File. File printf. Instead of printing to the standard output, the screen, the console, the terminal, whatever, then you can print to an actual physical file on the file system, right? As physical as it can be, I suppose. It's just a bunch of data, so it's just a bunch of electronic signals, right? So let's go ahead and take a look at an example here. I want to print a bunch of data. So if I've got an integer, 42, double pi equals 3.14159, my name, say, char, name, Chris, Bert, whatever, right? If I want to print everything to a file, well, I can just go ahead and go fprintf. This is a simple sentence, right? And the line if you really want to. But that's printf. With fprintf, you need to provide a new argument to begin the function. The file that you want to print to. And by the way, is in a good name for a file that you're writing to? Probably not. Let's go ahead and go with out. Right? And then close out. Right? So I'm going to print this simple sentence here. And let's take a look at data.txt. This is a simple sentence, and that's the end. There is a second line here. Why? Because I had that end line character. Right? I added this end line character right here. If I want to, I can go ahead and put more stuff, right? I could put in 3 end line characters. This is another simple sentence. Right? And then if I want to do actual data output, I can say fprintf out hello %s. Your number is %d and the line. And then I can use the same placeholders that I've been using with printf this entire time. Name and x. Right? fprintf. Also, pi is about %f. Let's only go with 3 digits of accuracy here, or of precision, excuse me, not accuracy. Precision and accuracy are different things. But we'll go ahead and print that. And what are the contents of the file now? When I do this, of course, the old contents were overwritten. And there. I've got 1, 2, 3 blank lines. Right? This is another simple sentence. Hello, there's my name formatted. 42 formatted. And there's pi out to 3 decimal places formatted. Right? All you need is printf. And you're good to go. Okay? Let's go ahead and put this into our examples. See why I said that this is going to go quick? Because a lot of the stuff that you are already familiar with, especially memory management. Opening up a file basically is like allocating memory. Closing a file is like deallocating memory, freeing up memory. And output is simply just printf. Now, here is the one that takes a little bit more, or a little bit new stuff, right? File input. File input. Right? There are many ways to do file input. Right? I'll keep it simple and show you the 2 easiest, most, I guess, useful ways. Right? There are lots of very dangerous ways of doing a file input that will result in buffer overflows. I'm going to show you the 2 easiest ways of doing it, and the 2 safest ways. 2 simple, easiest, useful, / safe ways of doing it. So we'll focus on 2 functions. One of them is fgetC, and the other functions fgetS. So by now you can see the pattern. Anything dealing with files is going to have an f in front of it. Get simply means I'm going to get that from the file. In other words, I'm going to do file input. I'm going to pull that out of the file and input it into my program. C and S stand for a single character, C, and S, what do you think that stands for? An entire string of characters, the entire line in the file. All right? So fgetC gets a single character from the file and advances the file pointer to the next character. Right? I.e., it reads 1 byte at a time. Right? It returns the character it read. Right? But of course, eventually you're going to get down to the end of the file, right? How do you know that you're at the end of the file? Well, it can't return null because there could be nulls in your file. Instead, when it gets to the end of the file, it returns this super special character that doesn't even appear in the ASCII text table. Right? When it reaches the end of the file, it returns a special character called EOF. Right? This is not a valid ASCII character. It is not something that is printable. It is system dependent. It is just a special flag value that your system uses to denote that the end of the file has been reached. What do you think EOF stands for? EOF stands for end of file. All right. So let's go ahead and take a look at an example here. I'm going to go ahead and get rid of most of this. Input file, that one that I just wrote, let's go ahead and open it up and read it now. Right? Remember, here are the contents. Right? So I want to read that by character by character. And whatever I want to do with that character, I'll just print it out. Processing it means that you could read it in and then output it to another file, read in 5 characters and then put that into a buffer and do something with it, whatever. I'm just showing you the basics of reading the file. Processing, that's an application that you'll get into in your hack this week. Okay? So let's go ahead and process it character by character. Char C is equal to F get C, and then you pass in the file that you're reading from. By the way, down at the end here, I want to close it. Right. And let's go ahead and print that out. Printf read %C and the line C. Right. Let's do that a couple of times. Let's read in the first 4 characters. Okay. And print them to the standard output. Oops. What did I do wrong? Well, I need to read the next character. And I can't declare that again. There we go. Input for writing. Oh. Do I want to write to it? I want to read from it. There we go. Let's make sure. Darn it. Undo. I can't do undo. That's all right. I need some text. Here's a trick. Lorem ipsum. If you're not familiar with that term, it is a term where it's just a bunch of random Latin phrases and words. It's simple dummy text of printing and typesetting industry. If somebody is doing some graphical layouts or something, they'll grab a bunch of lorem ipsum text because their job is not the content. Their job is the layout and the presentation. So you can go ahead and grab a bunch of lorem ipsum text, or you can have some fun with it. Say lorem ipsum Star Wars? Star Wars quotes, maybe? Come on. There we go. I'll just cut and paste this. It's just random quotes from Star Wars. So you can, traditional lorem ipsum text, of course, is not approachable because not many people know Latin. But hey, we can go ahead and have a bunch of Star Wars quotes. Right? That'll work. Right? So I want to open this up for reading. I will read in the first character, the second character, the third character, and the fourth character. And then I'll just print them out. Right? Let's find out what that is. W-E space D. That, in fact, is what is in there. We don't serve their kind here. Right? The droids. Right? So how would I adapt this so that I'm not doing character by character by character, cut, paste, cut, paste, cut, paste? I would want some sort of a loop, right? What kind of a loop? Do I know how many characters are in the file up front? Probably not. So which one would seem more appropriate, a for loop or a while loop? A while loop, okay. While C is not equal to the end of file character, go ahead and print it out and read in the next one. There we go. There. Character by character by character. Now this is going to be rather long, but so be it. Right? What was the last one? Accelerator period. Oops, not that, but over here. And what was our last, oops, there it is. What's our last one? Accelerator period. Then it reached the end of the line, end of the file, in fact, right? So I read it character by character by character. That's actually quite expensive because file I/O is expensive. If I'm only doing this character by character by character, then I'm flushing a buffer every single time, right? Actually doing file input or output is way more expensive if you're actually writing to the disk. And so you would not want to do like write to a disk character by character. You would want to wait until you have a bunch of stuff to write to the disk and then write it once so that you're only paying for that disk write once. Right? That goes a little bit beyond this course and gets into operating system programming and stuff like that. Don't worry about the details, though. So I will make sure that you have this as an example, though, in the notes. Right? That's F get C. F get S gets an entire line of the file, right? Up to a maximum number of bytes, characters, right? So let's take a look at the signature for this function here. Oops, there you go. Man F get S. Right. Come on. There we go. There is the signature. And now let's talk about its inputs and its output. Right? The first input is the buffer or string that you want the result stored in. Right? It reads up to a full line and stores it in S. Right? So it's your job to make sure that that S is big enough to hold any line that could be in the file. Or you can make sure that you're paying attention to the second argument, right? The second is the limit, right? It reads at most size minus 1 bytes from the file, right? So if you want to limit it, if you've got a buffer of, say, 1,000 bytes, then you put in 1,000 as the second argument so that it reads at most 1,000 minus 1, so 999 bytes. Why that minus 1? What does it need to do? The null terminating character, exactly. Minus 1 because it needs space for the null terminator character, which it takes care of for you. Nice, right? So finally, a function that does all of the work for us, right? Instead of, say, strncmp, the byte-limited versions of string copy and string concatenation, they don't take care of the null terminating character for you unless it sees it in the first n bytes, right? Finally, the third, it should be obvious. It's the file stream that you're reading from. The third is the file you are reading in, right? The file pointer you are reading in from. Right? The return value is a pointer to the string, the resulting string. In other words, i.e. S, upon success. Right? Upon failure, in other words, upon failure or the end of the file, well, it can't return EOF anymore because EOF is a char. Technically, it's an integer. But what can it return? What's the only thing that it can return to indicate I'm done? There's no more to read here. It's returning a pointer. So to indicate that it's done, what's the only thing it can return that's special? Null, right? On failure or the end of the file stream, it returns null. Okay? Note that also the end line characters are not preserved, not included in the read input. Right. So let's take a look at an example and see all this behavior at once. I'm going to go ahead and do the same file here because we're familiar with it. Right? There's actually 1, 2, 3, 4, 5 lines. So I should expect this to iterate 5 times if I do something like this. First of all, I need a buffer, right? Buffer that can hold, that is large enough to hold any line that you might read. Ooh, those are pretty long lines, right? How many are there? 671 according to this. So even though this is long lines, I can create a buffer of size 1000. That's not that big, right? Char buffer 1000. Right. That's big enough for anything in this file. What happens when I double everything up, though? Now that line is 1,344 characters long. Is that going to work anymore? Nope. Okay, so bump it up to 10,000. There's always going to be a bigger file. There's always a bigger file out there, right? There's always a bigger line out there. For most things, this is going to be sufficient in this class at least. But this is still dangerous in that you could end up not reading the entire line. In which case you'd have to put in some extra checks that did you actually read to the end of the line? If not, then you need to be careful, right? Actually, I think I did the notes wrong, but we'll find out here in a second. Yeah, this last one, I'll put in a question mark. Let's find out if I was right or if I was wrong, right? So here's my character buffer that's large enough to hold anything. And let's undo that so that we're only at 672 characters. So let's go ahead and get the first line. Char s is equal to forgets of, now what are the 3 arguments again? Well, they're down here. This is the string that you want to read into, in other words, my buffer. This is the maximum number of maximum number of characters that you want to read in. In other words, it'll read in at most 1,000 minus 1 to take care of the null terminating character for you. That's out of convenience. So if you've got a character buffer here of 1,000, just put in 1,000 right here. If it were 10,000, then you could put in 10,000 over here. If it were 10,000, do not put 20,000 in here, because then it'll read twice the size, up to twice the size. But in any case, it will stop at the first end-line character, all right? And then the final one is the input file that you want to read from in. Right? Now let's go ahead and print this out. In fact, let's go ahead and get rid of this while loop and just do the first couple of lines here first. So printf line is equal to %s and the line, and then s. And then let's read it in again and print out the second one and the third one. Of course, I can't have that redeclaration there, or that redeclaration. There we go. So let's read in the first 3 lines and see what it does. Right. Obviously, it's line breaking because this is these are too long of lines, but we don't serve their kindness here. Blah blah blah. Gets to the end, prints out a blank line. Where did that come from? Then the second line in the file is a blank line, right? So it prints out a blank line, and then another blank line. Right? Where is that extra blank line coming from? Well, it's coming from this. If I get rid of those, what does that tell you about whether or not the end-line character from the file is preserved by forgets or not? Let's find out. So, what does that tell you about the end-line character in the file? It's preserved. What did I write? End-line characters are included in the red output or input. Excuse me. If you don't want them, then chomp them out. How could I chomp that out? I could make an if condition. If the last character is equal to the end-line character, I could chomp it out. Chomping is, eating, right, or chewing on something. Chomping is, I think it comes from Perl, the programming language called Perl. That they have a chomp function where it takes out any trailing white space, and trim, left trim, right trim is another term for it. So let's go ahead and chomp it out. If the last character in S is the end-line character, how do I translate that into code? S sub whatever is equal to the end line character, then chomp it out, dot, dot, dot. How do I get the last character? If there are string length, if there are 5 characters, 0, 1, 2, 3, 4. So where's the last one? String length -1. strlen of s -1. If that's equal to, and of course you could write a function to do this. And in fact, you could start at the end, and if there are 3 end-line characters, then you could chomp, 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 chomp until you get to the first non-white space character. Right? How do I chomp it out? S of the same is equal to, how do I just get rid of it? The null terminating character. Right? Chomp it out. Very technical term here, chomp. It's not technical. All right. That starts to form a loop for me. If I want to read it in, print it out, then chomp it, or chomp it and then print it out, right? Then all I need to do is take this and wrap it up into a loop. Now the first one, of course, will be done by itself, but while some can not at the end of the file, dot, 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 read it in, or chomp it out, print it, and then set ourselves up for the next iteration here by going s is equal to forgets again of buffer 1000 in. There we go. So it's the exact same call as up here. It's just that I want to set up my while loop with that first call. So how do I translate this into code? Well, I'm not at the end of the file. If I'm at the end of the file, what does forgets return? Null, right? So should I check to see if it's equal to null? While it's not equal to null, then I haven't reached the end of the file yet. Only when forgets returns null does it say, okay, you're null, so there's no reason to chomp it out, there's no reason to print it out, and you jump out of the loop here. Right? Let's try this. There we go. Hit the accelerator, blah, blah, blah. And of course, I don't have an end. I chomped out the end line character here, so now this is all one big line right there. There's no end line character at all because I ended up chomping that out and I'm not printing it. So if I want to restore it, I can put it back in when I print it. And I will get some nice formatting here. Right, there we go. Line, empty line. Go to the next line. Luke, Luke, Luke. Have you seen Luke this morning? Blah, 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 blah. Right. Looks like Aunt Beru is speaking. Right. All right, no Star Wars fans either. So no Huskers fans, no Star Wars fans. Say what? I gotta check that. All right, good. All right. All right. So that's file input, file output, etc., etc. Right. The last thing that I want to do today is, because it is in your lab tomorrow, is to talk very briefly about binary data in C. Right. So first of all, binary data should, sorry, go back to the notes here, be handled by libraries. Right? Think about what you mean by library data. You mean images. You mean audio. You mean video. Proprietary data that has been saved directly as binary or something like that, right? Bring in a library to do that. Remember on hacks, I think that hack 5 and 6 and 7, in fact, when you were working with images and doing image manipulation, we brought in a library to do it because we didn't want to have to write codes to support JPEGs and PNGs and GIFs and whatever else, right? We brought in a library to do all that for you. Now, we did what was called glue code. We brought in that library that handled image formats itself, and then you had like 2-dimensional pixels. We wrote the pixels, and then we wrote the glue code that brought those two libraries together, right? Just to simplify it, because otherwise, I believe that library handles images by having one big giant integer array, and then like here's the first row, and then right next to it is the second row of pixels, and then the next row of pixels, and each pixel was represented by 3 integers, which were RGB values. So you had to do a lot of arithmetic to get to the right RGB value. In fact, it used RGBA, which is red, blue, green, and an alpha channel. An alpha channel means that it can be completely opaque or it can be completely transparent. Or it can be halfway between. 50-50, like 50% transparent would mean that you'd be able to see through it, and whatever's behind it would bleed through. We didn't want to burden you with those details, so we wrote some glue code so that we could simplify it and just talk about pixels instead. All right? But otherwise, that's binary data. In fact, if you look up on, let's say, Wikipedia, GIF, what is the GIF format? It's not just a bunch of pixels. There's actually, where's the formatting here? There we go. There's actually metadata at the front. The very first items here are GIF89A. That is called a magic, well, it's a magic number basically, that it's identifying this file as a GIF89A standard file. Right? In fact, let's download a file. Is this a, that's not JPEG. Why do you have a JPEG in the file? Let's see. I don't want to go searching around for random GIFs. Say what? Yeah, but that's animated. I don't know if that'll be very, very good. It is GIF. It is not GIF. Whoa. Come on. Here's an example. Hopefully this is an example. Yes. All right, let's save this on my desktop, foo.gif. Use GIF. All right. So, oh no. All right, it was saving as something else. So, view image. There we go. That will save as a foo.gif. There we go. Replace it. All right. I think you could just drag and drop stuff into the CS50 IDE, right? Let's bring that in. All right, there we go. And oh, I need to make sure that you have this in your notes. So let me go ahead and bring this over, and let me switch back to reading it character by character. And only partly here. So let's open up that GIF file. Right, or it's, what was it, foo.gif, right? And let's go ahead and read in the first few, right? So red, there we go. 1, 2, 3, 4, 5, 6, 7, 8. Well, we'll just do 8 here, right? What do you see? GIF89A space, and then a bunch of, then you start getting into other metadata there. So every binary format has some sort of prescribed standard. That the GIF format actually has this metadata up front, and then it has a palette table, which is also metadata, because it doesn't actually have RGB values. It has this pixel is a lookup. This pixel is pixel number 52. Well, what's pixel 52? You go to the lookup table, and oh, well, pixel 52 is a red pixel. Pixel 54 is a blue, half red pixel or something like that. It's because GIFs are actually really, really compact. You're only allowed up to 256 colors. And by limiting that, it limits the file sizes. JPEGs are different. JPEGs use some lossy compression techniques. So it takes and it samples, a bunch of pixels, and it says, well, use this Fourier transform over here or something to approximate this, so that when you decode it and you display it, you can actually use this math over here to reproduce all these pixels. It doesn't actually store it stores some pixels, but it doesn't store all the pixels. PNG is a lossless pixel for pixel representation, I believe. And you can put compression on PNGs, but uncompressed PNGs are pixel for pixel representations of images. You can see how complicated it gets. So again, if you are ever actually really dealing with binary data, bring in a library to do it. Right? Unless you're writing the library, in which case then things get really fun. Right? But What I do want to show you is that binary data can be a lot faster, a lot more efficient, and a lot smaller than text data, especially if it's only intended to be consumed by a computer. Right? C provides two functions to do binary I/O. One of them is fread. So fread is file read, right? And fwrite, which is you're going to write a binary file, right? So let me just go ahead and grab the for write here. Right, there we go. Oops. Why are you, there you go. Come on. There. So for write here takes several inputs here. I think it's 4, right? 1, 2, 3, 4. Yeah. Here is a pointer to the thing that you want to write. All right. So in fact, let's just read the this is the size of each thing that you want to write. These are the number of things that you want to write, and this is the output stream that you want to write to. Don't worry about that. Let's go ahead and look at an actual example here. You still open up a file the traditional way, output.bin, right, for writing, and make sure that you close it as well. But if you've got, say, a bunch of things that you just want to dump in binary, let's go ahead and create an integer array here, int numbers. In fact, let's do primes. How many primes are there going to be? 2, 3, 5, 7, 11, 13, 17, 19. How many was that? 8, right? Int n is equal to 8. So what I'm going to do is I'm going to write all 8 integers to the output file at once. So I'm going to go ahead and go with for write. And these are the 4 things that it takes. A pointer to the thing that you want to write. Well, the thing that I want to write is primes. And it's an array, so therefore it's its own pointer. The size of each thing that you want to write, well, each thing that I want to write is an integer. So what's the size of an integer? Size of int. The number of items that you want to write, how many items do I want to write? 8 or n in this case. And finally, the output file that you want to write to. Okay? And that's the last thing, the file star right here. Okay? Once I've done that, then I can close it. Right? All I've done is written 8 integers to this file, this binary file. Okay? Let's take a look at what it looks like. Demo.c, a.out. And you see that there's this new output.bin over here. If I ask the file system, what is that? It's data. I don't know what to do with it, and I don't know how to display it. If I try to more it, it's not printable, right? If I try to open it up, it's probably, oh, there we go. It's just a bunch of binary, right? It's not going to let me interpret that as text. If I look at how big it is, how big do you think it's going to be? How many bytes is this file going to be? Very small. Why? How exactly how small? 8 integers. Each integer takes 4 bytes. 8 times 4 is, help me, 32, right? 32 bytes. Right? Hey, 32 bytes exactly, right? Awesome. But I can't read it, right? It's not plain text. I can't open it up and look at it and read it as a human. Of course, a computer could do this. All you would need to do is use for write or for read and the exact same thing here. But we won't do that. Instead, what I want to do is for write. Let's do the exact same thing here, but we'll do it as regular output. Output text. There we go. And output.txt for writing. Instead of using for write, I will go with for int I equals 0. I is less than n I plus plus. Fprintf %d end the line. You don't have to end the line, but of course then you have a bunch of numbers that run together, and where does one start, where does one end? We could go ahead and put in commas instead, CSV data. Right. I'll just go ahead and use end line characters here, and we'll print out prime sub I. And then close make sure that for close, oops, sorry, what was it called again? Out text. fprintf to out text. Make sure that you close out text, and let's look at both of these things together. All right. So output bin, I still can't read it. It's unchanged. Right? It's still 32 bytes. Right? Output.txt though is 2, 3, 5, 7, ... How many bytes is that? Each character now is a byte. Each endline character is a byte. Right? So lsla output.txt. It's even less, but that's only because these are all single or two-digit numbers. What if I made them much larger? What if instead I did 2.147 billion, 1, 2, 3, 1, 2, 3, and 1, and 2, and 3. Doesn't matter. I could do the same number here. Right, that's 8 of them, right? Yeah, that's 8. They're not primes anymore, but we'll just keep that name for now. There we go. Take a look at output bin. Still can't read it. But over here, output.txt, much larger numbers. Now, what's the file size? 88 bytes versus, what's the original still? It's unchanged. It's still 32 bytes. Right? So in general, this is this is human readable, but it's going to be way less efficient. It's going to be way less efficient to read and write because a computer can do binary way faster than a bunch of text data. What it has to do, I mean, at the end of the day, it's still binary. But what it has to do, it has to read this in as a string, then convert that string over to an integer using A to I or something like that, and you're paying for that, right? So if you just have pure binary data, then stick with binary data. But if you have binary data, you should be bringing in a library anyway. Right? Okay. Make sure that you have this in the notes. Any questions? Let's check online. How do you pull up a man page in the IDE? It's just man. Right? So clear this out. Man, and then whatever you want to search for. Man, F, get S. I forgot what it was all about, and then you can go back, you can scroll up and down with your arrow keys. You can search for keywords using K. I don't know, file, right? And a whole bunch of stuff will come up here, and then you can, anything with the keyword file in it, it came up. Man, keyword. Let's be more specific. stdio.h. Okay. Okay, stdio right there. Standard input library functions. So if I don't have the keyword, I could probably just bring that up. Yeah, that'll bring it up. Right. But stdio with a keyword brought up a whole bunch of other things. Let's see. Nope. Just arguing about GIF or GIF, right? And it is definitely GIF. Right? Why? Because it stands for Graphic Interchange Format. Graphic, right? It's not a peanut butter.
The guy who made GIF say it was GIF?
I don't know. Who's the guy that made who made GIF? Who made this GIF? Okay. Stevie White. So I'm sure the pronunciation of there's a whole Wikipedia sub-article on this, right? The creators of the format pronounce the word GIF with a soft G, as in Jim. Steve White says that the intended pronunciation deliberately echoes American peanut butter. So, so they were going for a joke there, but no. Just because you create something, once it becomes popular enough, just like Star Wars, once it becomes popular enough, it's no longer yours, right? So we can still rag on the both the sequels and the prequels. I'll make sure that you have this in the notes, though. All right, but we can't rag on Mandalorian because that's awesome. All right. All right, then. We'll pick it up here next time. But that's all for file I/O. Again, simple because you already have all the tools at your disposal except for file input. When we come back next time, we'll start talking about encapsulation and creating our own user-defined, what are called structures. Being able to group pieces of data together to create new pieces of data. Okay? All right. Have a good lab tomorrow.